Hey everyone, welcome back. In this video we will be discussing section 4.5, which is all about L'Hopital's rule. L'Hopital's rule gives us a new method to evaluate limits under certain circumstances. In many ways it is a bit out of place between 4.4 where we were graphing functions and 4.6 where we will be applying the optimization techniques that we've learned all throughout chapter 4. As a result, many instructors choose to move this section to later in the course. To accommodate that, this video will assume that you've only made it through 4.4 and will not reference any section that comes after it, even if you've seen it. The topics in this section will rely heavily on taking derivatives of various functions. Make sure you are comfortable with taking derivatives of all the different functions we've seen in this class. If not, take a minute to go back and review that. Like I said in the introduction, this section concerns itself mainly with taking limits that were difficult for us before. As you see in front of you, there are 4 limits that were amongst the harder limits we had to take in this class. So what makes them trickier than other limits? The first limit has the property that both the numerator and denominator go to 0, as x goes to 0. The next 3 limits all have the property that both the numerator and denominator go to infinity as you take the limit as x goes to infinity. The worst part of all is all these limits have different values. Now, while we learned to deal with the last 3 limits by looking at the leading coefficients, and maybe your instructor derived the value of the first limit or just gave it to you, the question remains, is there a better way to deal with limits like these? As with all things in life, it's a good idea to start with a simpler version of the problem. All 3 of these limits have the same property as the sine of x over x limit did before. Both the numerator and denominator go to 0. But notice in this case, all these limits are equal to 0. So why is that? So let's take a look at the graph of y equals x, x squared, x cubed, and x to the 4th to see if there's anything we can figure out from the graph to help us answer this question. So what do we see? Now let's look at the graphs carefully. First of all, notice they are all going to 0 as x goes to 0. However, notice that the larger the power of x, the quicker the function is getting to 0. For example, the line y equals x goes straight into 0. Y equals x squared looks like a parabola, so it dips into 0 quicker, and then y equals x cubed and y equals x to the 4th go towards 0 even faster. This makes sense, right? Because if you plug in the value x equals 1/2 into all of these, the first one gives you y equals 1/2. The second gives you y equals 1/4. The third one gives you y equals 1/8. And finally, the 4th gives you y equals 1/16. Each one is smaller than the previous one, and that's what we're seeing in the graph, and that's also what we're seeing in the limit. The numerators are getting to 0 quicker than the denominator. That makes this limit equal to 0. You might ask, how does this work if the denominator is the function reaching 0 quicker? Well, it works much the same as any limit that we took before where the denominator went to 0 and the numerator didn't. But if you remember, this was kind of a mess. Sometimes it could go to positive infinity, sometimes it could go to negative infinity, and sometimes it didn't exist because one side did one thing and the other side did the other. Here's 2 examples. In the first one, there is no limit of x over x squared as x goes to 0, but x over x squared does have a left and right-handed limit at 0. In the other example, x squared over x to the 4th has a 2-sided limit as x goes to 0, and it's infinity. For simplicity, in these early examples, we will stick to situations in which the numerator goes to 0 quicker, so we don't have to deal with the various possibilities when the denominator goes to 0 quicker. So the third possibility is that the 2 functions go to 0 at roughly the same rate. So here you see 2 examples. The first one is looking at the lines y equals 3x and y equals x, both of which go to 0 as x goes to 0. You might argue that the line y equals x is always below the line y equals 3x, and as a result should be getting to 0 quicker. This is why I've been putting quotation marks on the word faster or quicker every time I use them. What's really happening is the rate at which y equals 3x and y equals x go to 0 are a constant multiple apart. If you think back to 2 slides ago, with x and x squared, there is no constant by which you can multiply x to get x squared. Another way to think about it is that they're both lines, and 2 lines go to 0 at a comparable rate, namely the ratio of their slopes. Hopefully this second graph further emphasizes my point. Here we see two parabolas, y equals 2x squared and y equals x squared. While it looks like y equals x squared is always below y equals 2x squared, they are getting to 0 at a comparable rate. In this case, the ratio of the two, which is 2. While this all sounds somewhat arbitrary, I'll throw out there that many of you will at some point have to study different computer algorithms. One of the things you will study is the rate of growth of the computation time of these algorithms as your data input gets bigger. That idea is identical to what we're talking about here. Okay, so this is all well and good when we're talking about powers of x. But what does this look like when we're looking at functions that aren't polynomials? Well, let's go back to that first example we started with. The limit as x goes to 0 of sine of x over x. I've graphed both y equals sine of x and y equals x on the same graph. These graphs are by far not to scale. I stretched the x coordinate so that we could see what was going on more clearly. Notice as we get closer to 0, the function y equals sine of x looks more and more like the line y equals x. In fact, it crosses 0 like the line y equals x. That's what we mean when we say that the limit as x goes to 0 of sine of x over x is 1. To further emphasize this, let's look at the limit as x goes to 0 of sine of 3x over x. We saw before that this is 3. But let's examine why this should be true from our new point of view. Once again, I've graphed y equals x, and this time y equals sine of 3x. But this dotted line you see is the line y equals 3x. Notice that the line y equals sine of 3x looks like the line y equals 3x as it crosses. So it should come as no surprise that sine of 3x over x should be equal to 3, since sine of 3x is crossing like 3x. Let's look at one more conceptual example before we jump into the computations. We want to talk about the limit of 1 minus cosine of x over x. I've graphed them both here, and if you notice, it seems like the graph of 1 minus cosine of x is getting to 0, more like a parabola or some higher power of x. So it seems like the limit of their ratio should be 0, since the numerator is getting to 0 quicker than the denominator. This limit is in fact 0, and many of you may have computed it back when you worked out the derivative of sine of x. It doesn't matter whether or not you did that, we are going to use our new tools from this section to compute it again. So finally, let's brainstorm what it was about x squared, x cubed, x to the fourth that caused them to go to 0 faster than the lower powers of x. I think the most interesting thing to notice is that each of those functions progressively have more and more derivatives that are 0 at 0. Using the notation given here, we see that f of 0 is 0, however, f prime of 0 is 1. Now for g of x equals x squared, we see that both g and g prime are 0 at 0, but g double prime at 0 is 2, which is not 0. Notice that the functions that get to 0, quote unquote, faster are the ones that have more and more 0 derivatives. This is actually a really important idea in mathematics, and it's heavily tied to a topic you'll see in Calc 2, namely Taylor series, or Taylor polynomials. Make sure to ask your professor to explain the connection between L'Hopital's rules and Taylor series when you're in Calc 2. I think we can all agree that as nice as this is, it would be a pain to have to graph two functions every time we wanted to understand the limit of their ratio. So we ask, is there a way to rewrite these observations symbolically? L'Hopital's rule gives us a connection between the limit of a ratio of two functions and the ratio of their two derivatives. It says that if you have two differentiable functions that are both 0 at the same point A, if you want to find the limit of their quotient, it is going to be the same as the limit of the quotient of their derivatives, provided the second one exists. When you have a situation like this, where the numerator and denominator are at 0 at the point you're taking a limit, we say that that limit has the indeterminate form 0 over 0. I want to be clear. The expression 0 over 0 doesn't mean anything. It is just a way to refer to this indeterminate form, or a form of a limit that cannot be computed as written. I will point out how this is related to our thought experiment after we've seen a couple of examples of this theorem at work. So now let's jump into several examples. In this class, we will use L'Hopital's rule primarily as a computational tool, despite it actually having some pretty deep meaning. So let's go back to the limit we had a couple slides ago. The limit as x goes to 0 of 1 over cosine of x over x. We conjectured using the graph that this limit should be equal to 0. Let's see if we can confirm our conjecture using L'Hopital's rule. So even though this is our first example, pause the video and try to figure out how to use L'Hopital's rule in this case. Okay, so the very first thing you should always do before using L'Hopital's rule is to verify that your function is in the indeterminate form that you need. In this case, notice that if I plug in 0 into the numerator, I get 1 minus 1, which is 0. If I plug in 0 in the denominator, I also get 0. That means this is in the indeterminate form 0 over 0, and L'Hopital's can be used. So how do we use L'Hopital's? Well, it says that the limit of the original quotient, because it's in an indeterminate form, is equal to the limit of the quotient of the derivative. Before I continue, I would like to point out some notation that I'll use throughout this video. Make sure your instructor is okay with using this notation in your own work. So this notation is simply this L'H above the equal sign. In this video, this will be above any equal sign when L'Hopital's theorem was used from one step to the next. Okay, so to use L'Hopital's, all we have to do is take the limit as x goes to 0 of the quotient of the derivatives of the top and bottom. The derivative of the top is simply sine of x. The derivative of the bottom is simply 1. So this is equal to the limit as x goes to 0 of sine of x over 1, which is 0. So we were right when we guessed that the limit was 0 back when we were looking at the graphs. The other thing we conjectured back then was that 1 minus cosine of x appeared to look like a parabola as it went to 0. One way to check it is to find the limit of 1 minus cosine of x over x squared. We will do it shortly with L'Hopital's rule, but first I want to point out that sometimes when you're taking a limit, it is necessary to use L'Hopital's rule more than once in the process. So once again, pause the video, give it a try, and then we'll do it together. So first we check and see that both the numerator and denominator are 0 when you plug in 0. That means this is in the indeterminate form 0 over 0, and we can use L'Hopital's. So we go ahead and do it. We take the derivative of the top and bottom and get that the limit as x goes to 0 of 1 minus cosine of x over x squared is the same as the limit as x goes to 0 of sine of x over 2x. At this point, we could use the fact that we know the limit of sine of x over x. But because the purpose of this video is to practice L'Hopital's rule, and our limit still has the indeterminate form 0 over 0, let's go ahead and use it one more time to evaluate this limit. So the derivative of the top is now cosine of x, the derivative of the bottom is 2, so we see the limit is 1/2. So this is great because it once again confirms our conjecture that 1 minus cosine of x was going to 0, like a parabola. After these two examples, I feel we can better understand what I was trying to say earlier. Notice, in some sense, when you use L'Hopital's, you keep differentiating the numerator and denominator until one of them is non-zero. Let's look again at the limit as x goes to 0 of x cubed over x squared. Notice that if I were to apply L'Hopital's to this limit, after two derivatives, the denominator would just be a 2, because the second derivative of x squared is 2, while the numerator would be 6x, which is still going to 0. This is why the more derivatives that are 0, the quicker the function will go to 0. Just remember, sometimes the derivative also doesn't exist, such as the square root of x, but L'Hopital's will still apply. Okay, this video has already gone on way too long, so I guess we're going to have a part 2 to this section. See you all then.